Hello everyone, we'll be talking about flavor quantum numbers and generation of the standard model. So what is standard model? It's basically a name given to the theory of fundamental particles and how they interact in 1970s. At that time, it had incorporated all that was known in that standard model. In total, there are 17 named particles in the standard model. It's basically divided into fermions, that is the particle that give matter, bosons, that is a particle that give force. Here we have gluon, photon, double boson, and Z boson, and then we have Higgs boson, which gives mass to everything. Coming back to fermions, it's further divided into quarks and leptons. They're different from each other because quarks can interact with the strong force, and leptons cannot. In quarks, we have up quark, down quark, a top quark, bottom quark, strange quark, and charm quark. And in leptons, we have electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. So all these particles are different from each other when we consider their spin, their charge, color, and obviously their mass. There's also something called generations, which we'll learn next.
So the standard model can be looked at in a different way, a division based on what we call the generation or the family. It is much like the generations that we are familiar with, but instead of a time-based generation, this is much more like a mass-based generation. And the higher the generation, more mass the particles have. But all the other properties like the electric and strong interactions remain the same. Basically, there are 3 generations in the standard model as of now, and each generation has 4 particles. For fermions, 2 quarks and 2 leptons. The first generation consists of the up-down quark and the electron and electron neutrino lepton. And the second and third generation basically made up of the heavier cousins. These heavier generations can only be found in high energy environments like the cosmic rays or the particle accelerators, and they decay quickly into their lower generations because of much lower and more stable energy levels. This is also the reason why much of the stuff in the universe, the observable matter is made up of the first generation particles. So the question comes, why are there only 3? Is there a fourth or fifth generation? The answer to that is we don't know yet, and scientists are trying to figure it out. The quantum chromodynamics actually limit the number of generations to 9, but says nothing about the lower limit. The main conflict is supposed to be the electroweak precision observables data, but with new data coming in every day, nothing is ruled out yet. And if there is a fourth generation, it is supposed to behave differently with the Higgs field than the present generations. So the existence of the fourth generation could offer possible solutions to problems such as the flavor changing anomalies, and maybe gives a better understanding on the baryonic asymmetry problem. So it is a very interesting research topic that's ongoing right now. That being said, there is another way to look at all of the particles of the model, that is through the quantum numbers.
Quantum numbers refers to the value of the discrete and conserved quantities of a quantum system. The quantities can be energy, moment, charge, baryon number, and lepton number. The quantum system can be an atom, an electron, or a subatomic particle. For example, the electronic quantum numbers are the values which provide solutions that are acceptable by the Schrödinger wave equation of the hydrogen atom. The electronic quantum numbers are principal quantum number, which designates the principal electronic shell of the atom and is denoted by n. Orbital angular momentum or azimuthal number, which describes the shape of a given orbit and is denoted by L. Magnetic quantum number is which corresponds to the total number of orbitals in a subshell, and orientation of these orbits is denoted by ML. The electronic spin quantum number gives insight into the direction in which the electron is spinning and is denoted by MS. Now let's delve into the flavor quantum numbers.
Flavor quantum number is the internal quantum number which describes about the type of the particle and its interaction with other particles through the fundamental process. Which all the fermions have this quantum number. There are 5 flavor quantum numbers in quarks. They are isospin, charm quantum number, strange quantum number, top quantum number, and bottom quantum number. In isospin, it is the strong interaction. It is represented by I3, in which the third component is only conserved. It has the value of plus 1 by 2, plus or minus 1 by 2. Up quark type has plus 1 by 2, and the down quark type has minus 1 by 2. Sharp quantum number is nothing but the difference between the number of charm quarks and charm antiquarks. The value of the plus 1 as the number of will be 0. Strange quantum number is the difference between number of strange antiquarks and the strange quarks. The value will be minus 1. For the top or truth quantum number, the difference between the number of top quarks and the top antiquarks, the value will be +1. The bottom and the beauty quantum number, the difference between the number of bottom antiquarks and the bottom quarks with the value will be -1. We have a Brayon number where B is equal to 1/3 into a number of quarks minus number of antiquarks. It is not a quantum number, but it gives the specific values to the all 6 quarks flavors separately. And we have derived quantum numbers. They have hypercharge and the electric charge. Hypercharge is the sum of the all quantum numbers except isotopy, and the Brayon number is included. This is why this is represented by Y. Electric charge is the number of isospin and half of the hypercharge. That is Q is equal to I3 plus half of Y. Now let's see about leptons.
All leptons have a lepton number of 1. Electron, muon, and tau have a weak isospin of -1/2. Electron neutrino, muon neutrino, and tau neutrino have a weak isospin of -0.5. In addition, we also have a quantum number called weak hypercharge, which is -1 for all leptons. Leptons have 6 flavors of quantum numbers: electron number, tau number, and muon number, and their associated neutron numbers. And then, in addition, we also have a separate quantum number called electronic lepton number, ionic lepton number, and tauonic lepton number. Electronic lepton number has a value of 1. Ionic lepton number has a value of 1. Tauonic lepton number also has a value of 1. Electronic lepton number gives a value of for electron and electron neutrino. Tauonic lepton number gives a value for tau and tau neutrino. Ionic lepton number gives a value for muon and muon neutrino. Neutrinos can be transformed into another flavor from one flavor. And then the mixing of these neutrinos can be called as PMNS matrix. And then now let's talk about the conservation in flavor quantum number.
Flavor conservation. What is conservation? In a layman's term, if we see, conservation is nothing but the amount of matter entering a system equals the amount of matter or mass leaving the system. So in a similar manner, if we remove this term mass and replace it with flavors or flavor quantum numbers, it basically tells us the flavor conservation. Although it's not very technical, I'm telling in a general manner. So there are different forms of flavor conservations. It can be categorized under quarks and leptons. Under quarks, if we see, flavor conservation basically comes under charm quark, then strange quark, then top quark or truth quark, and beauty or bottom quark, which are conserved under strong and electromagnetic interactions, basically. So in terms of leptons, if we see, in terms of leptons, various flavor quantum numbers are electron lepton number, then muon lepton number, tau lepton number, as we all know. And these numbers are conserved under electromagnetic forces and weak interactions. So the conservation actually can be understood in another perspective, which is these conservation are actually related to some sort of symmetry, which is basically the Noether's theorem. So flavor symmetries are nothing but they are most common in hadrons, basically, in which these strong forces don't distinguish between several flavors, and it acts equally on all these flavors, particularly showing equality. Actually, not only there are only flavor conservation, even there are many more conserved quantities.
In analyzing the nuclear reaction, we apply the many conservation laws. Nuclear reactions are subjected to classical conservation laws for momentum, angular momentum, or energy. A baryon number is also a conserved quantity. A baryon belongs to the category of hadrons, which experience a strong interactions. Baryon consists of three quarks like a neutron, proton, sigma, or lambda. The history behind this proposition consists of the three quarks. History behind this is very interesting one. Initially, it was proposed the axiom due to observation of protons being so stable. Protons were conserved to have a half-life longer than the universe. Now we know heavier baryons decay to lighter baryons, therefore protons should theoretically never decay actually. A theory, however, was proposed before the discovery of the quarks. Now we know baryons made up of three quarks. Each quark is given 1 by 3 baryon number, and each anti-quark is minus 1 by 3 baryon number. So it's actually, this theory is more like a conservation of quark. So quark can't just vanish in any interaction whatsoever. Baryon number is conserved in all interaction of standard model. So conserve means the sum of the baryon numbers of all incoming particles is same as the sum of the baryon numbers of particles resulting from the reaction. The proton and neutron get a baryon number of +1, where the antiparticle counterparts gets a baryon number of -1, and all other particles gets baryon number of 0. There is another type of conservation part from baryon numbers such as mass energy conservation. Everybody knows, according to the Einstein equation, E is equal to mc square, mass and energy are interconvertible, especially in equal reaction. This is a more fundamental form of conservation called conservation of energy and mass. Now, this mass energy, however, conserve quantity throughout every interaction. This is so fundamental that it is just used to propose the theory of existence of neutrons. So till now, there is no experimental evidence that this violates this conservation law. So there is another conservations laws like spin and charge conservation.
So, hello guys, I'm talking about charges and spin. Charges corresponding to the time invariant of generators of a symmetry group, and specifically to the generators that commute with Hamiltonian. When a physical system has a symmetry of some sort, Norton theorem implies conserved current. The character that flows in this sort of current is actually called the charge. It is the generator of the local symmetry group. Now, the good examples of the phenomenon of charge in different, with respect to different forces in nature, are the color charge of quarks. The color quark generates the SU3 color symmetry of quantum chromodynamics. The weak isospin quantum numbers of the electroweak interaction, it generates the SU2 symmetry of the electroweak. And the electric charge for electromagnetic interactions. Now, talking about in spin, the spin is the intrinsic angular momentum associated with elementary particles. It is purely quantum mechanical phenomenon without any analog in classical physics. Spin is not associated with any rotating internal parts of elementary particles. Rather, it is intrinsic to the particle itself. An electron has spin even though it is believed to be a point particle possessing no internal structure. The concept of spin was introduced in 1925 by Ralph Krohn and independently by George Uhlenbeck and Samuel Goldsmith. Now, the angular momentum is a vector quantity describing an object in circular motion. Its magnitude is equal to the momentum of particle and the direction perpendicular to the plane of that circular motion. The existence of electron spin angular momentum is inferred from experiments such as Stern-Gerlach experiment, and which silver atoms were observed to possess two possible discrete angular momentum having no orbital angular momentum. Since elementary particles are point-like, self-rotation is not well defined. For them, this is equivalent to the quantum mechanical interpretation of momentum as phase dependence in the position and of orbital angular momentum as dependence in the angular position. Spin is quantized and only take on discrete values. The spin angular momentum of an electron measured along any particular direction can only take on discrete values such as multiples of h bar by 2 or negative h bar by 2. If we had an odd number of half integer spin particles, the result is half integer spin. And if we add even result as an integer spin. To complicate matters, the decay products may leave the point of decay with orbital angular momentum as well as spin, and it is this total that must be conserved. However, Orbital angular momentum are an integer times h bar and cannot change the total angular momentum from itself from half integer to integer or vice versa. Therefore, in the decay of an integer spin particle, there are zero or another even number of half number spin decay products. And in the decay of a half integer spin particle, there are odd numbers of half integer spin products. So the number of half integer spin particles in a decay is conserved. Now, all the quantities are not conserved in all interactions of nature. Now, moving forward,
we can see some unconserved quantities in certain interactions, like all of the previous conservation laws that they said don't necessarily apply for each and every case in the history of the universe. There's going to be some quantities that aren't following specific symmetries that are generated due to specific interactions. Like, for example, the weak force interactions does allow for the conservation of the weak isospin, but this does not allow for the conservation of any other flavored quantum numbers, such as the normal isospin. So the normal isospin, as we all know, helps distinguish between the up and the down quark. And now we all know that protons and neutrons can interconvert with each other. And this is only due to the fact that either an up quark converts into a down quark, which leads a proton to become a neutron, or a down quark becomes an up quark, which means a neutron becomes a proton. Obviously, the isospin here cannot be conserved if there has to be particular change. So particle change or the flavor quantum number change in this case is due to the weak interaction. Now, a lot of the things that are conserved in others, such as flavor quantum numbers and even some of the lepton number conservations are violated when it comes to weak interactions and specifically neutrinos. Now, lepton number conservation is an empirically derived fact. It isn't exactly, it doesn't have a theory behind it, but we have found recently we have found experimental evidence to sort of throw a wrench in the works of the lepton number conservation, at least in the types of flavors. This can be seen in the form of neutrino oscillations. You have a neutrino going through vacuum, and it's a superposition of electron neutrino, muon neutrino, and tau neutrino. So it won't have a single number that can possibly be conserved. So we can see that not all quantities are conserved in all cases, and there's going to be some other unconserved quantities, and we can only hope to find ways to further our understanding of the universe. Thank you. That will be all for our talk today.